Recording in progress.
Yeah, comes on everyone. Let's start off. Last thing we did was this. Pressure difference across the surface with different radius of curvatures. Interesting. Okay. Let's go ahead with more questions. Hope everyone has gone through the notes, seen the models there. Others, do keep your cams on. Arush, Abhinav, Arnav, Devika, cams on everyone. Let's go ahead with a question. So we got a plate and there is a liquid here. So like I said, the surface tension, right, makes you climb the wall. This is how the diagram looks, the side view. So this is the wall and this point A is just inside the liquid surface. Is just inside the liquid. Meaning if I have to draw the side view, are you able to visualize how is this there? This is how the 3D structure would look like. Where this is height h. So this point A is not actually a point. This entire line is point A, the side view what you're looking at. Is the question clear? So when you have a wall, because of the adhesive forces, the liquid will climb the wall. So the question is find h. So there are two questions: find the pressure at point A and find the height h of the wall. Let's get this. This would be a good one. This would be an advanced, maybe a more than one choice question. Anyone didn't understand the question, please ask me. Don't know how to do, take a minute, think about it. Then I'll give you a hint and then I'll give another minute. Anyone not clear with the diagram, please ask. Finding pressure at A is easy. Now you can't say this is P naught, okay? That is because At that point A, this is a curve, isn't it? So this will be like a part of a bubble, no? Do you know the radius of curvature here? So you can't say P naught. So how do we go about this? So we go from the bottom. Look at this. So on the liquid surface, the pressure here is P naught because this is exposed to atmosphere. If this is P naught at the same level, the pressure here also must be P naught because horizontally the same thing. Now, if this is point A just inside and this is height h, now if you're going vertically, what is the pressure here? If you go vertically, the pressure will decrease. So it is P naught minus rho g h. Easy. But the question is still, what is h? H is not, you have to still find h, isn't it? Is this thing clear, everyone? So you found the pressure there. So when you go from the bottom, it will be minus rho g h, right? Yeah. Is this clear? Now, how do you find h? I'll give you an idea. See, can you draw the FBD of this part in the horizontal direction? Meaning, I would just want the horizontal forces. Can you write all the horizontal forces on this piece, this liquid section, in the horizontal direction? Draw FBD of the liquid, right? In for all the forces in the horizontal direction. Vertical direction, we don't require them. I'll tell you. But try to draw horizontal direction. Take a minute, figure it out. See if you can get something from there. Just to give you an idea how the picture looks like, the picture kind of looks like, like this, isn't it? Like your curtain. If you see, this is your curtain, right? Paper. This is how you're pulling the surface, isn't it? This is how the surface looking, no? If you have your curtain, right? If you just imagine your curtain that you have in the house. So this top part is point A that is actually providing the support. If you just lift it like this, you can see this horizontal part. How is the horizontal part? Here the force is acting horizontally and here it is acting vertically. Can you see the surface there? It's like your curtain bending. This is how it is looking if you can see my screen. And it is all white, but yeah, this is the side view that you're looking at. Now, can you draw FBD of the horizontal forces on this part? No, that's not the answer. You'll get it in roots. D is the density, yeah? Okay. But how many forces are there? If you ask you, total, how many forces are there? See, one, this wall here is pushing, isn't it? Is the force due to the wall? The liquid is touching the wall, so wall is pushing it, no? There's a normal reaction kind of thing. Atmosphere is pushing here, atmosphere. Your own weight, mg. This part here, remember, just now I said it's like a curtain, so this will be surface tension T into L. The horizontal force, it's like a rubber sheet, isn't it? It is getting pulled. Similarly, there's also force here, which is T into L. Are you able to visualize that? So again, if you look at my screen, I'm asking you to draw the FBD of this paper. This is the front view that you're looking at. So for this paper, what are the forces? There is one force on this top, isn't it? That's your T into L. And there is one force in the horizontal direction. That will be again this length T into L. You're able to visualize? There are two surface tension forces. One mg, one force due to the wall, and one atmospheric pressure. Now can you draw? I'll give you another 30 seconds. Now look at this thing. So if you take this wall here, we know the force due to the wall will be nothing but pressure at center of mass into area. Do you remember this question in fluid mechanics we did? When a liquid is touching a wall, what is the force acting on the wall? You can just take the force at the center and finish it off, isn't it? Do you guys remember that? Take a small length dx at a depth x and then you integrate. This was done in fluid mechanics. So you can directly take the pressure at the center of mass and finish it off. This center of mass is at a height of h by 2. The force due to the wall will be, remember the pressure at the bottom is P naught. This will be P naught minus rho g h by 2. That will be L into h. So this full thing was h. And I'll take this length to be L, which is not given. That L should cancel out in the end. Similarly, if you look at this curved surface here, the atmosphere is acting like this, a constant pressure P naught. So there are two projected areas. So this is a projected area, this is a projected area. Do you guys remember projected area? A flat surface which will make an open curve into a closed surface. So this is P naught into the base area, which I don't know and I don't need also. Whereas this guy will be P naught into L into H. This is your projected area, the shaded one. So we are taking few ideas from fluid mechanics. So we have atmosphere pressure FATM, this pressure P naught into projected area L into H. The projected area is that rectangle. The wall is pushing from this side, F wall. This side, the surface tension is T into L. This is vertically upward. I'm not interested in that. The reason why I'm not taking anything in the vertical, can you find mg of this piece? We can't find mg. So that is the reason we are ignoring it. We can't do anything with the vertical because I don't know what is the weight of that piece. So we are ignoring it. But I'll just put it in the FBD. So this is also force due to atmosphere. I'll write it x direction and this is y direction. This is P naught into base area, which I can't calculate because I don't know. I don't have a data there. So if you just balance the forces in the horizontal direction, so we have F wall plus the surface tension force T into L is FATMX, meaning x direction. That is the meaning of it. So F wall will be P naught minus rho G H P naught minus rho G H by 2 LH plus T into L is P naught LH. P naught LH will cancel. L also will cancel. You'll end up with rho G H square by 2 minus plus T is equal to 0. We get H is equal to root over 2T by rho G. Check. That's your answer here. Do have a look at the steps. Main thing is that piece is in equilibrium, so you have to draw the forces in the horizontal direction. That's the main idea there. Any step you're not convinced, any FBD, force, projected area, anything that you're not clear with, please ask. How would we know that this approach is to be used? Now you know. Now you know. What you're asking, right? You're asking like, how will I know? It's like asking, how will you know what you'll do well in the future? You will never know, Rehan. The problem is that. So what we are trying to do, it's like asking me, sir, how will the advanced paper be? No clue. So what we are trying to do, we are trying to cover as many models as possible, as many varieties as possible, right? So tomorrow when you see something like this, for example, just to give you a variation, tomorrow the same question, they will say this angle is theta. What will change in the question? What will change? Now, see, this is what you have to figure out. You should not be asking what to do with the whole thing. You have an idea. If I modify something, you should be able to. What will change in the question, Bata? In this whole thing, what will change? Anyone? this TL, instead of being straight, this TL will be at an angle. तो एक horizontal component भी आएगा. So इस case में एक horizontal component भी add करेंगे, TL cos theta whatever. Clear? Bas, this is what you are trying to learn. You have a basic idea about a certain model. If something modifies or something happens, you know what to do. Or tomorrow, let's say the question was not like this. The shape instead of a wall, if it was a triangle, and then your liquid surface is like this. Meaning I couldn't draw well, but ऐसा कुछ है. Then what will you do? Story is still the same. You're getting it. So that is what we are trying to do. We are trying to learn one basic thing, one maybe a little different model. And what we are expecting is if something comes of similar sort or something similar idea, you should be able to get ideas from here and do it.
Yes.
That's it. So what you're saying is true. How will we know? It's first time if you see this question, you might not be able to figure out in the exam. That is for sure. No doubt about it. So that is the reason. That's what I keep telling everyone. Advanced paper, even though the paper is advanced and tough, if there are 20 questions, trust me, if you have done all the work in the exam, you must have seen 14 to 15 questions you must have seen somewhere. Don't think like you'll go to the advanced exam, then you'll think about each question and use your superior intellect and try to solve. Chance hi nahi hai. You'll run out of time. That 4 or 5 questions will be something new which you couldn't figure out. Fine, na? At least do this 14 properly first. That is the reason, right? If you're scoring 70%, right, you are getting into IIT Bombay. Who is asking you to get 90%? So you have that leeway. Clear? So try to cover as many models as possible. So we are doing so many different models in the class notes. You'll be practicing, and then we will have our revision program. So we will do a lot of stuff. You'll be writing a lot of papers. Things will be fine. Don't worry about that. Just try to learn and absorb. Clear with this? Meaning, think about it. Every question that I taught you, I'm pretty sure you must not have got an idea on how to do it. Did you know how to find alpha, beta, gamma? No, idea nahi aata hai, right? This thing, did you figure it out? No. But did you figure out this thing, viscosity and a pipe? So this is what I was saying. So you will learn. Next thing. Now, what you're asking is completely genuine. Everyone feels that way. So basically, that is how life is. It's like asking, which college will I get? No idea. Which job will I do? No idea. How much salary will they pay? No idea. How will my wife be? No idea. That is the reason people go to astrology. They feel like, someone will tell you like, their life is how jayega, like that, like this. And that is it. One day my mom took me to an astrologer like that. He came to the house actually, some famous guy it seems. I was least bothered. My mom, my dad, everyone went, and my mom also said, go, ask him. If you want to know something about it, he will tell you about your future. I went to him. I just sat down. I was a kid then. I was in IIT first year, I guess. He was like, you will do very well in life, that in life. I said, yeah, you need not tell me. I was thinking inside, I think you need not tell me all that. I know. Then I said, he told all stuff, regular stuff, meaning, tell me one thing. If someone is going to tell you like this, your life will be great, you will do well in life, but you will have some problems in life. Doesn't this look generic? And will you deny that your life won't be good? Will you tell him, who told my life will be very horrible? You'll not accept it, right? You'll say, okay. And he might say something like this, when you're a child, something bad happened. Then he doesn't know what bad happened. You'll start visualizing, that day fell down from the cycle, the dog came and bit me. Really bad happened, right? He predicted it. So the thing is, they'll just sell you something generic. You will figure out, you will try to fit the story. You will try to let every damn thing that can happen in your life to what he's saying, and you think, it is true, it is matching. He spoke for 10 minutes. I didn't give a damn about it because everything he was saying, I said, like, this thing, right? You would have told this to anyone, it would have been same. Best example, ना कभी देखा वो Times of India में पीछे आता है Capricorn, your day will be like this, Sagittarius, today will be like this. Next time when you get this, read all of them and you'll observe everything fits you. You just close the ऊपर का thing and read it, you will think everything fits you. So सब हो गया था. End में he asked me, you have anything to ask? You want to know something about your life? I said, tell me when will I die? I said, that is the most important thing. Bloody, if you tell me, right, when I'm going to die, meaning I can plan accordingly. If you're going to tell me I'm going to live 100, I will live the way that way. If you're going to tell me my lifespan is not there, then bloody why will I take a class today, right? I'll just say, boss, sorry, I have to go. I'll be with my parents and done. You will live quite differently. He's like, no, 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 we can't tell all those things. We should not know. I said, then what is the point? After that, my mom never told me to meet an astrologer. She got scared. I said, why do you ask such kind of questions? I said, it's a people do get scared when you talk about that. Oh, the people say you're jinxing it, but of course, that is the truth. So, anyways, so you'll never know. All you can do is guess and continue prepare as much as you can and plan for it, and that's it. And things will fall in place. That I have observed. Every time I used to get scared, what will happen with this project, what will happen with this, but things fall in place. All you can do is your work. That's what Lord Krishna said. Focus on your work, do your work, let the result take care of itself. You don't worry about it. Getting back to this. So if you remember in the beginning when we had that force profile we are talking about, there were three molecules. The one inside the liquid, these things were useless. They had a net force 0, they did nothing. Whereas the whereas like as molecules on the surface, they had a net downward force. That is what created the surface tension, the membrane property. The third molecules are the ones on the corner. So if you see, we have the F cohesive forces and the F adhesive forces due to the solid. So what are cohesive forces? This we did discuss before. These are the forces between the like molecules, like the water, liquid, whatever. So these things are going to do something. So if you actually try to draw the FPD of this liquid here, we will observe the F adhesive is acting horizontally, and by symmetry you can see this F cohesive is like this somewhere at a 45 degrees. So if F adhesive is greater than F cohesive cos 45, then what will happen? The interaction between solid and the liquid is stronger than this thing. So the liquid will actually rise up. You will see the liquid climbs the wall. Like the previous question that we did. These kind of substances are called wetting substances. Basically, they wet the surface. Example, water and glass. So whenever you put water in a glass, the edges actually rise up. It's pretty small, but it is there. But if the adhesive forces are weaker than the cohesive forces, if cohesive cos 45, then the surface would look like this. The surface actually gets depressed like this. This is like mercury and glass. These are called non-wetting substances. Like if you put a plastic or water, it's a waterproof substances. These are. You take your cotton cloth and water, it's a wetting substance. It just absorbs everything. So cotton water bonding is stronger than water bonding. But we take water on a plastic sheet, you will see water bonding is stronger than water plastic, so it forms a separate droplets. So this surface, right, how it looks, let me show you a picture that would give you a better visualization. There. Now, that is not blood, but anyway, you can imagine it is blood, looks interesting. So there on the left hand side is a red colored water. You can see the surface how it is, a concave. On the right one is a mercury and a glass. You can see the convex part. This is what will happen when you put it in a thing. So this is Hg, mercury and glass. This is some red colored water. Plain water you wouldn't have been able to see. So did you ever went for a, not exactly a blood test, but if you see, right, when they poke your finger and they take a glass plate and they rub it across the glass plate and they put it under the microscope. Ever seen that? When they want to test your blood sample or something under a microscope, They take a glass plate, they put a drop of blood and they spread it. It spreads over so that you can clearly see that platelets or whatever is inside compounds more clearly. You need to spread it out. So if you take a glass plate and if you put a drop of mercury and a drop of water or blood, what do you think will happen? Not this one. It would look like this. Can you see? So that is mercury on a glass plate. The mercury, right, is a non-wetting substance. So all the mercury will try to stay together. Mercury-mercury bonding is greater than mercury glass. This is a non-wetting substance. So the mercury won't spread. It will become like a droplet. Cohesive is greater than adhesive. So mercury sticks together. Whereas this thing is a wetting substance. If you put a water or something on a plate, it spreads off because the interaction between that solid and the liquid is stronger. So what will happen? It will try to spread as much as possible because attraction is good. When you get attracted, that energy of the overall system decreases. So it's more stable. So in this case, adhesive force is greater than water cohesive. Is this making sense, everyone? Wetting and non-wetting substances. Any doubts on this page? All clear with this? So coming from here, we get something called a contact angle. So that is a more simplified version of saying that adhesive cohesive ka fight. So this angle, this is how we define. I'll give you some examples also. Angle between the tangents to the liquid and solid away from the liquid is called contact angle. Let me show you with an example. Now look at the word here. You can take them away from the liquid or towards. So basically, whenever you have a liquid, so this is a wall, this is the liquid surface. So at the point of intersection, you can always draw two tangents. Now look at this thing. So at this point for the liquid, I can draw tangent like this, I can draw tangent like this. Agreed? Now you tell me which one is away from the liquid? The right one or the left one? The right one, isn't it? The right one is away from the liquid. So this tangent here for the liquid is away from the liquid. This, and for the solid, you can draw tangent like this and tangent like this, which is away from the liquid. The upper one. So this is a tangent away from the liquid. This is contact angle theta. You're getting it? This is tangent to the solid. This is tangent to the liquid. And you draw both of them away from the liquid. The angle between them is defined as contact angle. Suppose if you take this and mercury and glass, away from the liquid is this, away from the liquid is this. This is contact angle. So this is mercury and glass, and if you observe, theta is obtuse. And here theta is acute. So acute contact angles mean they're wetting substances. These are non-wetting substances. So just looking at the contact angle, you can tell whether something is obtuse or this thing. Suppose if you take a mercury drop, this is mercury. Now look at the tangents again here. So for the liquid surface, this is away from the liquid. For the solid, this is away from the liquid. This is theta. Able to visualize how is the tangent? So at the point of intersection, you can draw tangents right or left or up or down, whatever. In that, one of them will be away from the liquid. Can you tell me these guys? Suppose if I take a liquid here and put some liquid inside, what is the contact angle for this? How will you draw? Suppose same thing. If the liquid is outside, then how will we draw? Suppose if the liquid is like this, how will you draw contact angles for this? So again, for the liquid here, this is away from the liquid, this is away from the liquid, this is theta. This is away from the liquid, this is away from the liquid, this is theta. This is away from the liquid. For the solid, this is away from the liquid, this is theta. Are you sure with those things? So at the point where the liquid touches the solid, so that in this case is this point, you can draw, just to give you again, for example, see this case, when the liquid is like this is the point of intersection. So here for the solid, you can draw, see a tangent is actually a line. Na? This is a tangent, isn't it? This is a tangent to the surface. So you take the tangent which is away from the liquid, this guy. For the liquid surface, this is the tangent, the green line. You take the one away from the liquid, this guy, and this is theta. Is that understood? Any doubts on these angles, please ask. There, now you know how to define the contact angle, and we know why we are getting a contact angle. So, clear? Next thing. So this phenomena, right, of the solid attracting the liquid and the liquid rising or getting depressed, this leads to something called a capillary effect. Now, in real life, we see this, but once in a while. But the reason is we need to have a very thin pipes in order to observe this. So these capillaries are nothing but thin pipes. They have a very small radius, something in like 0.1 millimeter or something. So when you take a capillary and place in a liquid, you can say on one end of a capillary, is placed in liquid with the other end in atmosphere. We observe the liquid rises. This is important. Huh? This is there for HSC. They'll ask you find the height of a capillary. Prove करके HSC में it's a 4-mark derivation. We observe the liquid rises. So let me show you the picture. This is the container. We have a liquid here, and let's say we got a capillary here. Capillary is nothing but like a straw, you can say. Only thing it is the radius is quite small, and this is what we'll observe. The liquid actually goes up to a height. So if you look at the data here, theta is your contact angle. S is the surface tension. Rho is the density. R is the radius of the capillary. So what we will do, let's draw the FBD of the liquid in the capillary. This is called force method according to HSC. But yeah. So if you actually just draw the FBD of the liquid, that shape will look like this. You will see a meniscus. This is called meniscus. That cup kind of shape which you're seeing, the technical name for this is meniscus, which you have actually seen in this picture here. This is a meniscus. Able to see this? This is what I was saying. It looks like this. It's not a perfect spherical thing. It's a part of a circle. So it's a meniscus, this bowl shaped thing. Now here, if you look at the forces acting, one is your mg. The height h is measured from here to the surface. So height h actually is measured from the bottom. Getting it? And if you look at the surface tension force here, the surface tension force is actually acting here. Can you visualize a trampoline? Imagine if you have a trampoline like this, and if you're standing in the middle, how will the trampoline pull you up? The forces are along the trampoline, isn't it? Like this, like a cone shape. Can you see my screen? This is how they will look. The forces will look like this, a trampoline. Just imagine yourself standing on the trampoline. What will happen? The surface will bend like a meniscus, and the trampoline is pulling you up in this direction like a cone. So if you actually look at the forces here on this meniscus, this is your contact angle theta. This is your contact angle theta. This is the length we are talking about. So the surface tension force will be surface tension into 2 pi r, the length, into cos theta, the vertical component. So that would be the surface tension force which is pulling up. So this is the reason why the liquid is going up. And here we neglect this small part of the liquid that further we have to actually integrate. So we neglect this, it's too small. So we say since the liquid is in equilibrium, 2 pi r s cos theta is equal to mg. This is a solid cylinder of liquid. So mg is nothing but density. Volume of the cylinder is pi r square hg. So from here we get h is equal to 2s cos theta by rho g r. A standard formula you should definitely remember. Mains of bits, it's a direct result. But this is how we derive it. So if you see the height of this, the liquid that rises, it depends on this. Just have a look at this. Let me show you something that will give you a better clarity. The reason why we don't see this in real life is because, think about this. Density of water is 1000. Gravity is 10. Surface tension of water is very small, 10 power minus 3, 10 power minus 4. So you already have a 10 power minus 6, 10 power minus 7 in the numerator. So if you take a pipe of 1 centimeter, you will get a height of 10 power minus 5 meters. That is like 0.01 millimeters. You can't see. You need to have very thin pipes in order to see this effect, appreciably. But look at the picture there, the FBD. Again, we just did an FBD there. Let me show you how this would have looked. There, see. Now, in fluid mechanics, we studied if you take a U-shaped pipe and if you pour liquid, we should get the same height. But did you notice something here? The height is not same. So if you look at the formula, h is equal to 2s cos theta by rho g r. H is proportional to 1 by r. So smaller the radius, more the height. So this thing, if you can see, it's a very thin radius in here. So in fluid mechanics, right, we didn't consider this thing. In fluid mechanics, the answer would have been same. All would have got same height. It shouldn't have mattered what is your radius. But if you include surface tension, it would matter. So smaller the radius, more the height. This is how the liquid will rise. And here you can see the radius is quite large. So this is a negligible capillary effect. There, have a look at this picture. So capillary action does happen, but in order to see that, you need to have a really small radius to see that thing appreciably. So the formula which you calculated, right, was this actually, the height from this normal level. So this extra height you got is because of surface tension. Let me use red. This screen is bad. Because still here, the fluid pressure will balance the heights. The reason you got that extra height is because surface tension. Is this picture clear, everyone? Any doubts on this page, please ask me. All clear with this? So the result is more important for an entrance perspective, but there is also another way to prove this. It is also important for HSC. They'll ask you, there's something called a pressure method. There are two ways you can prove this. And HSC people have seen, they're asking this, find the height of a capillary action using pressure method. So they specifically mention which method to use, and you have to use that only. So this method is pressure method, meaning the concept, the idea is also important for us. It gives you something little different data. So when you take this meniscus, and when you look at this surface here, this is not a complete hemisphere, it's a part of a sphere. So the idea was this. If you go and stand here, and if I ask you about this surface, what will you think? You will think this guy belongs to a big air bubble, isn't it? You will think that curve is actually part of a bubble. So observer will feel observer thinks there is an air bubble there. So he will think I'm inside the water and there's an air bubble inside. So according to his logic, so this pressure will be P naught. So he is outside and P naught is inside. So this is P concave. So at this point A here, PA, the pressure will be P naught minus 2S by R. Now be careful, this R is different from small r. This is capital R. This is small r. This is theta, this is theta. Meaning I'll just show that again. So if you look at that surface there, this was the meniscus. This is capital R. That is a radius of curvature. Exam they can ask you this. Find the radius of curvature. People will get confused with the radius of the pipe. This is radius of curvature of surface of meniscus. Whereas this thing, small r, is the radius of the capillary. Both are not same. And we know from contact angle, with the vertical, this angle is theta, so this angle will be theta. So we have a relation between them. R cos theta is equal to small r. Quite a useful relation, comes a lot. So if they ask you find radius of curvature, don't get confused with radius of capillary. So then you're done actually. So at this horizontal level, the pressure is P naught exposed to atmosphere. So this also has to be P naught. And this height is H. So pressure at A, PA plus rho GH must be pressure on the surface, which is P naught. This is P naught minus 2S by R plus rho GH is P naught. So from here we get H is equal to 2S by rho G capital R. But be careful, this is not small r, this is capital R. If you substitute in terms of small r, you get 2S cos theta by rho G small r. Same formula. But we have taken a completely different approach. We used the excess pressure in a soap bubble concept. Here, this was equilibrium problem. The surface tension force is balancing mg. It is more easy to, feel it. But unfortunately, HSC I saw this question being asked many more times compared to the force method. You should know both. But in terms of entrance perspective, the radius of curvature is a pretty good concept. So do have a look at this. There, this is how you can prove this two ways. But end of the day, if you see the result is important, there's only one result there, 2s cos theta by rho here. Check it out. Any doubts on this? Yeah. Next thing. So when I was in 11th, right, my sir taught till here. And the time got over, and I said, okay, we'll continue tomorrow. And he left. Can you show the previous slide? Okay. Then after he left, right, when I saw this thing, I got a brilliant idea. I said, yeah, there is something interesting happening here. I can use this and we can get something. And I made a plan for it, meaning this is what I thought. So I said, I'm going to make a, I'm going to take a container, I'll put liquid inside. Now, let's say if you take a capillary normally, and you'll get a height of, example, 5 centimeter. Then what I said, okay, instead of putting 5 centimeter, what happens if I keep only 3 centimeter? You're getting it? Normally the water will go to height of 5 centimeter, but if I keep only 3 centimeters, I will get a fountain, right? Then I said, okay, great, I got a fountain. Then what will I do? I'll put one more container here. I'll put millions of capillaries. So all this water will come and accumulate here. Then I will put one more container here. I'll put one more capillary again of 3 centimeters. Again, liquid will overflow here. I'll put one more container like this. I'll put millions of capillary. I will raise the water here. Then I'll put a turbine here. And this water will run the turbine. I'll get electricity. The water will come back again and again will go. So this way I created a engine where, I can get infinite power supply, isn't it? The only cost is construction. Once the construction is done, there is nothing. I'm not burning coal. I'm not using nuclear fuel. I'm just getting electricity out of nothing. So I said, like, yeah, it's a brilliant, super idea. Then I went home. Then I started thinking, right? I took some nice A4 sheets. I started making a full presentation. I started writing, formulas, that, this, kitna cost hoga, kya hoga. So the plan was this. I'm going to take a patent first of all, because if you don't have a patent, someone will steal the idea. So I'll get a patent on this thing. I didn't get a name for this. I thought I'll think about the name later on. So then I will build, every city I will build a power plant and I'll supply power, right? If the government is supplying for 5 rupees, I can supply for 1 rupee, right? I'm getting for free of cost. And within few years, entire India, I'll be the one supplying the power. I'll be the world's richest man. This was the plan. Hearing it? So I wrote a full report of 8 pages. Now the biggest problem that I have is I don't know how to get a patent. कहेंगे प्लान सब रेडी था इन्वेस्टर मिल जाएगा एक बार पेटेंट के बाद and so then I thought okay next day sir will come right after the class gets over I'll go and ask him sir I hope to get a patent. Now the problem is when I say patent he will ask na what is there so I have to show him something so I wrote everything down. So next day morning I went super excited. I didn't even get proper sleep. I went early to the class. I was waiting. Then sir is yet to come. My friend was there. He asked Arun, what happened? What happened? Kya hai? I said, idiot, get out from here. Because of you backstabbers only, like, things have been like this. He was looking at me like I'm some mad person. Movies hota hai na, hero, your hero ka friend steals the plans and he sells it to enemies and he becomes rich and all. So movies zyada dekh liya tha. But then I was clear, this idiot is going to steal my plans. I told him, I'm not going to tell you anything now. Once I get the patent, once we start the factory, if I want, I'll make you the general manager. Don't worry. And that guy was looking at me. तुझे क्या हो गया? मतलब, what are you talking? What patent? What general manager? He has no clue what I was talking about. But I was sure once he sees the plans, he will backstab me. करके हो गया. Class started. Getting it? I was just waiting, like, let the class get over, then I'll show the sir. Next day, class started, and the first topic sir started was a tube of insufficient length. This was the exact plan that I had. What happens if you keep a tube of insufficient length? So first I'll tell you what happens. So first thing, if you keep a tube of insufficient length, the liquid will completely fill the tube. And unfortunately won't get a fountain. The liquid completely fills up the tube and doesn't overflow. I heard this statement and I was like, what? I said, because look at the whole plan that I made, right? If the liquid doesn't overflow, how will the liquid go to the next container? And if it doesn't go up, why will it flow down? And if it doesn't flow down, who will run the turbine? And if the turbine doesn't run, where will I get the electricity from? The whole plan was going for a flop. Then I said, maybe sir could be wrong. But then again, this is what happens when your dreams get shattered. I was in complete shock. I was like, what? Yesterday I sat for bloody 4 hours. I made a lot of dreams. My friend also was supposed to be my general manager. Then then I said, okay, let sir explain something will be there. We will figure out a loophole in this. So let's see what happened exactly. Why will the liquid won't overflow? Why will our power plant ka whole idea goes for a toss? So imagine if you put a pipe here, and just for convenience, let's imagine if in a normal case, this would have gone to 10 centimeters. So now what I suggested, let's put a pipe of only 3 centimeters. So what happens is the liquid will rise till the top, everything same radius, everything same. You will see there's no overflow. Now you need to get back to the story why the liquid started going up in the first place. Now when you take this full pipe, the pipe of sufficient length, and when you actually see the FBD, ask yourself, how are the forces? The cohesive forces were like this. So there was a F cohesive force. The adhesive forces are like this. So the F adhesive force became more than this, it went up. Now look at the insufficient Chupka container. The problem here is once the liquid reaches the top, tell me one thing, who is making you go up? The solid surface, isn't it? It's like this, because there is a wall, I'm able to catch the wall and climb. What if there is no wall on the top? Who is going to make me go up, isn't it? There is nothing here to attract the liquid higher. Why will the liquid overflow? And worst case, that same force which is actually making you go up, F cohesive. Now look at the adhesive forces also. They also look like this. F adhesive is also downward, you're getting it. Just imagine your trampoline. Huh? See, if your trampoline is like this, when you're putting a weight, it is pushing down. What if the trampoline, if you try to pull the trampoline out, won't it bulge like this? When it tries to come out, that same trampoline which was pushing you up will start pulling you down. You're getting it. So let me show a picture how it would have looked. There, can you see this thing? If you try to put more liquid, can you see the bulge there? The same surface tension which was actually pulling you up till now will actually start pulling you down. Look at that thing. It doesn't overflow. It forms a bulge like this. You get a bulge like this. So that same 2 pi rs cos theta which pushed you up now is pulling down. Is that making sense? So here there is no solid surface on the top to attract the liquid molecules higher. So there is no way the liquid will go up. Maximum you can fill the top and stop. That looks like a reasonable explanation. The whole reason you started going up is because there is a solid. Once you reach the top, there is no more solid. So in this scenario, the solid had a certain amount of force. It can pull only this much height. So if you put a tube of insufficient length, you are not going to overflow. So there's no solid surface above the liquid or above to attract the liquid. Right. So it won't go up. And worst case, if liquid tries to go up, the same adhesive force will actually pull you down. It's like a fixed, that rubber sheet trampoline. You go down, it'll push you up. If you go out, it'll try to pull you down. So if liquid tries to go up or go out, the surface tension pulls it down. Clear with this? Fountains are something else, record. Fountains, you need to apply enough pressure. If you apply enough pressure from the bottom, this bubble will burst. You have to apply enough pressure for that to happen also. So the formula will be H dash. So the formula is still valid, 2s, but what will change is the contact angle. 2s cos theta by rho gr. So the edge of the insufficient tube is different from a regular one. So contact angle is different. So the formula is still valid. The contact angle will adjust in the formula to get a new height. We'll talk about that also. In a fountain, if you don't apply enough pressure, liquid won't come out. If you keep a hole in the middle of the tube, use such metal suspension, same thing will happen. See, if you make a hole here, what do you think will happen? You'll get a bubble here. If you can't break that surface tension, liquid won't come out. Like I said, na, in entire fluid mechanics, we ignored this. Remember the velocity of efflux wala? I make a hole here, liquid will come out. That's not going to work. See, I'll tell you how. If you take this thing and imagine you make a hole like this. So when the water tries to come out, first you'll get a bulge like this, isn't it? Ever seen ketchup? It forms like a bulge. So if this pressure is P naught, यहाँ पे pressure कितना होगा? P naught plus 2S by A. Right? That means for this water to come out, if you take this height to be H, this is P naught. This is the next question we are going to do actually. So P naught plus rho GH is P naught plus 2S by A. Means you need a height of 2S by rho GA, which is actually the height of the meniscus capillary in order to first break this bulge. You getting this? So if you take a container with a hole and if you put water, liquid won't come outside till you reach this height. All you will get is a small bulge out here and then that's it. Is that making sense? So your velocity of efflux formula will go for a toss. Clear with this? That way. So the edge of the tube is insufficient. Insufficient tube is different. Therefore, the contact angle is different. So after listening to this, I was convinced it won't overflow. I was shattered. And then class got over. My friend is still looking at me. I said, take the papers. You get the patent. You die somewhere. I gave it to him. And then I left. I went home. I was so depressed for 2-3 days. Then I started a new project, how to destroy the earth in 10 different ways. I wrote for almost I figured out 4 different ways. I did some project on that. 4 different ways I figured out how to destroy Earth. One was killing the ocean algae, throwing a nuclear bomb into volcanoes, all that nonsense stuff. And after 30 days, I said like, yeah, Earth bhi kya kiya na mistake. Let it be karke forgive the Earth also. Then I understood that's how villains are made. When the dreams are broken, you go into a very villainous path. So that is what happens when you don't have Instagram, PUBG, Facebook, and all. You sit there and do all this kind of random stuff, creating perpetual motion engine. So what I created, right, was called a perpetual motion engine. Perpetual meaning these things work without taking any energy, but actually they give you energy. They don't exist. Clear with this? Tube of insufficient length. There. So there's a tragedy whenever I teach this concept. But then again, happens. Next thing. When the liquid goes up, it gently goes up, right? Where is it coming out with force? Right, Arya? When you put a straw, you're saying you're sucking the, when you're pulling it, right? You're pulling the air out and creating a vacuum. If you just put a straw, water won't come out on its own, right?
Yes, sir.
That way. Now, if you pump the water with a machine or something from the bottom, that's a different story. You're giving excess pressure to break the bubble on the top. The end of the day, that is the story. You need to give excess pressure to break the bubble which forms. So in this case also, there's a heat produced. So here, if this was the surface here, if this was the height h, this was the center of mass to a height of h by 2. And we know this meniscus is being pulled up with 2 pi rs cos theta. And we also know this 2 pi rs cos theta is responsible for balancing the weight mg. So here the work done by surface tension force will be force into displacement, which is 2 pi rs cos theta into h. And I know 2 pi r cos theta is mg. So this is actually mgh. But what is change in potential energy? That is mgh center of mass. This is one thing in nature you'll always observe. You lost half the energy here. Even in the most efficient thing that you can create, you will always lose 50% energy. This you will notice not only here, happens everywhere. You take a rubber band, stretch it, at least half of the energy is lost in heat. You take a battery, charge it, half of the energy is lost. You take energy from the battery, again another half is lost. That is one of the reason why batteries are more, highly inefficient to store energy. When you are, let's say if you put 100 watts, you lose 50 watts, you store 50. Again, I'm talking about very efficient. And when you try to recover that 50, you lose again 25, you get 25. So even the most efficient battery you can create will give you only 25% efficiency. But in real life, even that also you won't get. You'll get maybe like around 10, 12%. That is the reason, storing electricity in a battery and trying to use it later on, it doesn't work. It's not economically feasible. You lose too much. There, you lose half of the energy. This is one thing in nature. There is no free lunches. You're getting something, whenever there's a conversion of energy from one form to another form, you always lose energy. So when you're running, right, more than half of the energy is just lost in the form of heat only. You actually barely use 30% and actually trying to propel yourself. Think about it. When you're getting down the steps, why do you feel tired? Climbing the steps, you get tired, I understand. Getting down the steps also, you get tired because every time your leg hits this thing, it stops, right? All that kinetic energy becomes heat. So that heat has to be dissipated. Your body becomes warm. You need to start sweating. Even climbing down the stairs require a little amount of energy. It is easy, but still. Clear with this? So there. So if you see this whole thing, there are primarily three important things. One, the formula HS2SR cos theta by rho gr. Second, cube of insufficient length. So if you keep a height less than h, you are not going to overflow. Third, there is a heat produced. Let's see a few questions. Any doubts on this so far? Great. Let's see a question. We have a U-shaped pipe here. This radius is R1. This radius is R2. S is the surface tension. Theta is contact angle. Rho is density. So when you pour liquid into this, this is H2. This is H1. Find H2 minus H1. Now, in fluid mechanics, if you ignore surface tension, both would have been equal. But the surface tension won't let them be equal. They do get messed up. Find the difference in heights of a U-shaped tube. Meaning the one easiest way that you can actually guess the answer easily. Think about it. If there was no surface tension, both would have had same height. Because of the surface tension, this guy will go how much extra? 2s cos theta by rho g r1. This guy will go how much extra? 2s cos theta by rho g r2. So what is the difference? Subtract them, isn't it? Making sense? That would be an easiest argument you can make and figure out. That would be the answer actually. But you want to solve, this is how you go about it. We have to go with the pressure method, if you remember again. So if you take this, so it will form like a bubble here. If this is P naught, this is P naught. So here the pressure will be P naught minus 2s by R1, but I know R1 cos theta is small r1. This is P naught minus 2s cos theta by r1. Similarly here it will be P naught minus 2s cos theta by r2. This point is B, this point is A. Since they're at the same level, PA is equal to PB. This height is H1, this height is H2. So this will be P naught minus 2s by R1 cos theta plus rho g H1 will be P naught minus 2s by R2 cos theta rho g H2. Little lengthy, but the pressure method will give you the answer. P naught will cancel. You end up with H2 minus H1 is 2s cos theta by rho 2 minus rho g R2. 2s cos theta by rho g R1. So basically the height of a meniscus wala formula. But that argument is making sense, right? If the thing would have been same, the heights would have been same. Because of the surface tension, you're getting the height extra height. So just subtract them and you're done. Clear, everyone? Next one. Next one. We have a capillary. The liquid went up like this. To a height h. The radius of this capillary is a. Now what you did, a rod of square cross section of side A is immersed in the middle. Like this. Look at the picture. You kept the rod exactly in the middle like this. Then something happened and the liquid went up like this. And if you look at the top view now, you will see the circle here and you will see this, the square cross section like this. Able to visualize the picture? So assume surface tension, contact angle, everything is same. Find the new height. So this liquid will go to a new height, h nu. Assume s theta is same. Find h nu. And if you're thinking exactly what's happening there, just to give you an idea there, when you keep the square thing, the liquid will also start climbing the square plate, isn't it? Able to visualize? Just like the wall problem we did today, not only this thing 2 pi rs cos theta is there, now you also have this square plate, the force pulling up, isn't it? So that will create an extra force in the upward direction. So this is how it will look. I hope the picture is clear. Is the scenario clear? You have a capillary of radius, height is h. S is not given, theta is not given, all fine. Now you took it's like this, you took a square rod and kept it exactly in the middle. So that will generate extra surface tension force and the liquid actually goes higher. So find the new height in terms of H and A. How do we approach this? Hmm. Okay, let's see. The answer won't be that good. Now, initially, the first one when you take, when the liquid went up here, so the force that was pulling was 2 pi, radius is A, S cos theta. This was mg. So here m was density, pi a square h into g. So we have 2 pi a s cos theta is mg. Perfect. Now in the second case, now when you kept this thing inside, understand this surface here, it started pulling in 4 directions here. So this liquid surface here started pulling this way, which is SA, the side is A, right? And you need a vertical component. So if you just, how do I draw this? I'll do one thing, wait, I'll just put only the edge. It's like this, SA, and we're talking only about the vertical component theta. So this will be SA cos theta. Like that, there are 4 of them. SA cos theta, SA cos theta, SA cos theta. Now, when you take the FBD with this rod in the middle, let's say the liquid is still here. So one, there is a force due to this guy, which is 2 pi a s cos theta. This is still there. Then we have the square frame ka force, which is 4 SA cos theta, that is balancing the new weight m dash g. Any doubts on the FBD? The square rod is also giving up and this thing. So now this will be 2 pi as cos theta. That is the surface tension due to that. 4 SA cos theta is equal to m dash g. But now you have to be careful here. So this m dash g is what exactly? This m dash g is density. What is the area? Pi a square minus a square na? You have to remove the square plate ka area of cross section, isn't it? The water is there only in this part, isn't it? There is no water in the middle part. Is that making sense, everyone? So when you take the area, you should remove this a square area from the cross section. Sure. So pi a square, there's the area, and minus a square into h nu into g. Perfect. So yeah, let's substitute. So from here, you can take SA cos theta. Na? So SA cos theta is mg by 2 pi. Mg is rho by 2 pi goes of a square hg. By 2 pi, perfect. So you can take out SA cos theta common here. This will be rho a square hg by 2. This will be 2 pi plus 4. That is equal to this. Rho goes off, g goes off, a square goes off. You will be stuck with h by 2. The 2 also will cancel. You will be like pi plus 2, pi minus 1 h nu. You can check the calculations. Pi plus 2 by pi minus 1. There, that's your answer. Because the end of the day, the answer is given only in terms of h, isn't it? There is no other information. A and theta are not given. I said assume s and theta are same. So answer should be in terms of h and a only. You don't even need r actually. But there are the steps clear, everyone. So the two major things here is the square rod provided the extra force. The square rod also decreased the cross-section area, so you can get more height now. Is this making sense, everyone? Clear? Let's see one more. Any doubts on this? Clear, Rehan? Puruja, Niharika? Clear? Arnav? Abhinav? Ansh? Adi? Vignajit? Surya? Sharman? Parth? Perfect. Next one. This is a good one. It's little lengthy, but solvable. Let's say we have a container. Let's say we have a capillary here. The liquid has gone up till here, height h. H is the height of the liquid column, L is the length of the capillary. Now what you did, you removed the capillary. You took the capillary out of the liquid. And liquid is gently poured inside. Meaning you took out this capillary here. This is also air. Now you started pouring the liquid here, drop by drop, drop by drop. Then we observe the liquid doesn't fall down, it actually gets stuck like this. This is the new height. Find new height. This will be a proper Menzel question. Is the question clear? So capillary, when it is in the water, height was h. Now you took out the capillary completely from the water. Now you start putting water, little drop, 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 drop. So some water gets stuck inside the pipe. You must have seen this, right? When you're drinking some cold drink or something, sometimes water gets stuck in the straw. So what is this maximum height that you can keep? Find h nu and find the force required to remove the pipe from the water. M is the mass of capillary. There, I kept two questions in this. Both are, each one is a proper mains level question. Think, take a minute. First was easy. Matlab, you have to think. S is not given, theta is not given, nothing is given. Answer will come in terms of this only. For the second question, you will need actually. First one answer comes in terms of H and L. Second one answer comes in terms of S theta and all that stuff. So what's the difference? When you take it out, what changes? Ask yourself, when you're inside, what was there? When the capillary was inside the liquid, the reason you went up is because of 2 pi rs cos theta. That was balancing your mg. Agreed, everyone? Now, when you take out this capillary, I'll just exaggerate the figure. Now, you tell me, when you pour the liquid, what do you think will be the shape? The liquid will be like this. You'll get one more meniscus now here. You'll get a bulge, isn't it? So now you have one surface tension pulling up. You have one surface tension pulling up. Now you tell me, if one surface tension can balance mg, then two surface tensions will balance 2 mg, isn't it? So you can hold a weight of 2h. Is that making sense, everyone? Yeah, but there is one thing you have to be careful. So the answer will be the new height will be 2h if the length of the pipe is greater than or equal to 2h. The answer will be L if length of the pipe is less than equal to 2h. Why is that? Example, देखो. Let's say h was 10 centimeter. Length of the pipe was 15 centimeters. Now, what is the meaning of 2h? I can balance up to 2h, right? That is the meaning, right? I can balance up to 2h, but what is the length of the pipe? 15. Isn't it? I can balance 20 centimeters, but the pipe is only 15 centimeters. So what will I do? I will just fill till the brim and stop, isn't it? Is that making sense? So here 2h is 20 centimeters. Therefore, liquid will fill 15 centimeters and stop. That is the answer. That is the answer is 15 centimeters. Can't go more than 15. Clear, everyone? What about the second part of the question? Is this making sense? Now, why didn't you get a meniscus here? The reason you didn't get a meniscus here is because it is liquid now. How do you define a surface? The interface of two mediums. This is liquid, this is air. You have a surface. Second question, when you're pulling the pipe out, what are the forces acting on the liquid? Again, same thing, same. The reason you're going up is because the meniscus is pulling you up. Now, if you draw FBD of the capillary by Newton's third law, remember this was force on liquid due to capillary. This is force on liquid due to capillary. So if you draw the capillary ka FBD by Newton's third law, if you're pulling the liquid up, the liquid will pull you down. 2 pi r s cos theta. This is force on capillary due to liquid. Makes sense? So liquid is pulling it up, but this is where people forget. There is one more meniscus. If you look at the liquid outside is also forming a capillary meniscus there. So there is one more meniscus here, which is actually dragging this way. That is also 2 pi r s cos theta, assuming the pipe is thin. Are you getting it? See, for the capillary, there's a liquid inside, there's a liquid outside. So there are actually two meniscuses. There's an inner meniscus, there's an outer meniscus. On top of it, you have your own weight mg. This is F external. So most people, right, forget that external meniscus. This is the force due to liquid on the outer surface. So this is the reason whenever you want to pull the pipe out of it, you have to actually exert force more than mg. That's what makes these are two separate mains level questions. So F external will be mg 2 pi r s cos theta 2 times. If the capillary has a thickness, then it will be 2 pi r1 cos theta, 2 pi r2 cos theta. Is this clear, everyone? So if something is inside the liquid and you want to pull out, you have to balance mg plus the surface tension forces. Any doubts on this? Clear? Take a break, come back to 711. Any doubts so far you can ask?
Sir,
Oh, yeah.
sir, isn't the mg already being balanced by 2 pi rs?
Okay, this mg is the pipe ka mass record.
Okay, that's it.
Mass of the capillary था वो.
Okay, sir.
I won't draw ना. See, FBD of the capillary में I won't draw weight, water का weight.
Yes.
Yeah. This is weight of capillary. Let's see the next one. So this is a good one. There are actually two main questions. Simple ones. You should know it theoretically. Next one. So we have a container with a hole. This the solution I already gave you. But let's see. Of radius A. So generally what we think, right? When you put this in a water, immediately water comes out. It doesn't happen that way. So as you're immersing it in a liquid, at a certain depth h, you actually get a bubble like this, and then the water flows. So S is the surface tension. So the question is find h when the water enters the hole, water enters through the hole. Let's get this. So normally when you take boats and all, right, the bottom part, when they weld it to metal sheets, you actually have a microscopic holes in it. So the reason why the water doesn't enter is one of these things. Surface tension actually stops them from it. So smaller the radius, more depth you can take inside. So microscopic holes have a radius of in micrometers. So kind of it works out. Now, just to show you how the shape looks, did you ever prick your finger for a blood test or something? How does it look? Do you get a fountain? That comes in Tom and Jerry. Tom gets hit with some rock, so you get a fountain. But normally, this is what a normal person gets. You can see that liquid drop, it forms a bulge like a bubble. It doesn't, you won't get a fountain. So something like this happens actually. Able to visualize? Get this? Easy one. I'll give you a minute. Let's see. So if you actually look at the hole, this is what you will notice. See. So as you're pushing the liquid, initially you'll notice the liquid is flat. Then you get a small bulge like this. And now if you look at the forces here, this will be a contact angle theta and theta. So the force here will be 2 pi a s cos theta. So here you can't change a, you can't change s, but you can change theta. So the one who is stopping the liquid from entering inside is this 2 pi s cos theta. So 2 pi s cos theta is, resists the liquid flow. So as you increase the depth, so as h increases, the contact angle changes. The contact angle decreases. Think about it. In the extreme case, what will happen? This will form a perfect sphere. In that case, the force will be exactly like this. This will be the maximum force, 2 pi a s cos theta. 2 pi s theta becomes 0. Is that making sense? Think about it. The only thing that you can change is theta. So 2 pi a s cos theta increases to resist the liquid. So as you push it more and more and more, the surface will bend, 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 and eventually it will become like a perfect hemisphere here. If you push anything more than this, now the bubble will pop. So if you look at the picture, this forms an hemisphere here. If this pressure is P naught, here the pressure is P naught plus 2s by A, it's a liquid drop. Here if it is P naught, here the pressure is P naught plus rho GH. And these two should be equal. The same thing just now I told you. The same thing you can do for velocity of a flux parting also. So we get S is equal to 2s by rho G. If you actually see, this is a meniscus ka formula, isn't it? Where the contact angle theta is 0. So this formula is same as height of the capillary. Clear? Next one. Any doubts on this? So if you make small holes at the bottom, you're still safe, but still don't do that. Next one. Now, if you ever go to a doctor, right, and when he prescribes you some, eye drops or something, did you see this? What the doctor says? Put 2 drops in your eyes. Don't you think when you're giving someone medicine, shouldn't you give a proper dosage? Put 2 ml, put 4 ml or something. Who tells you put 2 drops in your eyes? It looks so vague. But the point is, if the doctor tells you now put 3 ml in the eye and 4 ml in the eye, how do you measure? You put it in a spoon and take it. So that means now, for the simplicity for the consumer, the company who designed the bottle has to design it in such a way when you squeeze it, the amount of liquid that comes out should be exactly like each drop is 1 ml or something. So if you have a bottle like this, which is let's say filled with some that eye solution or whatever, so when you squeeze this, you will get a bubble like this. So as the radius increases, at certain point, this drop falls. So if you're making plastic containers for a medicines, you have to design them differently compared to making, plastic bottles for cool drinks. This is the radius of the drop. So here A is the radius of the hole. S is the surface tension. Rho is the density. Gravity is there. So as you keep squeezing this, at some point, this is the radius of the drop. It becomes too heavy and it falls. So find R when the drop leaves the dropper. So this is an eyedropper. Now for convenience, we will assume R is much, much greater than small a. So radius is small, so we can assume it to be spherical. In real life, it actually stretches, it bulges a bit. It's not exactly spherical, but we can assume that. Assume drop is spherical. So when you press, you can be sure that every drop that it comes out has to be a specific amount of quantity. Until unless you really press it hard and you make it like a water jet. How do you do this? Anyone not clear the diagram, didn't understand the question, please ask. Question is clear. Think about it. I'll give you another minute more. The main thing you need to figure out the contact angle actually. Let's see. Now, if you try to draw the video of this drop, see how it looks. We'll draw a big one. So this would be that A. So at this point, if you see, this would be the surface tension. That would be a tangent here. So this would be the center. This is radius R. This is radius A. This is your contact angle theta. That is theta. This is no, that is not theta. The vertical. This is theta. This is 90 minus theta. This is also there. Basically, this would should be tangent. I didn't draw it properly there. So if that is theta, this will be also 90 minus theta. There. So from little geometry here, sine 90 minus theta will be opposite side A by R. So we have A by R is equal to cos theta. So this was the relation which we got before also, that R by R will be always cos theta. So that is one thing. So now if you look at the forces here, the surface tension force is pulling this up, which is 2 pi A S cos theta. Right, and that is being balanced by mg. That's it. Story is simple. The surface tension force on that mouth is balancing the whole mg, isn't it? So we have 2 pi a s cos theta is equal to mg. But what is cos theta? Cos theta is a by r. And what is mg? Rho 4 by 3 pi r cube g. Pi goes off, 1 2 will cancel. You have a square s rho 2 by 3 r power 4 g. So we have r is equal to 3a square s by 2 rho g to the power of 1 by 4. So the main idea in the question is to find the contact angle. You're getting why I took that green line there? How is the mouth of the container? Look at the mouth of the container. It's like this, isn't it? If you remember the definition, it is the angle between the two surfaces. So for the solid, this is the tangent, no? And the liquid is this thing. So that is a contact angle. The angle between the tangent to the solid and this. That r is much greater than a is just given to make sure it is spherical, right? Or else this won't be a complete drop, isn't it? I wanted to neglect this volume to make it 4 by 3 pi r cube. That way, since r is much greater than a, theta actually tends to 0. But remember, see, whenever I say approximation, think of like this. If I got 0.01 by 1 plus 0.01, what does it mean? With respect to 1, you can ignore this, isn't it? It doesn't mean you'll ignore this and make 0 every time. Comparison. Is this clear, everyone? Any doubts on this? Yeah, next one. This would be a good question, an advanced one. Maybe a single choice advanced question. This next one will be an advanced paragraph question. This is a pretty good one. So we have a thin pipe here and we have a thick pipe here. This is a capillary. We can neglect capillary effect here. It is too big. So what is saying, they're putting the liquid drop by drop. Initially it is empty, you're putting drop, drop, drop. So then what will happen? The liquid will rise here. And the liquid will be something like this. So this height will be H2 and this height will be H1. Both the heights will not be same. Plot H1 and H2 versus time. So on the right side, you can ignore the capillary effect, but on the left side, capillary action does dominate. So plot height, how will the heights change with respect to time? It's a pretty good one. You should definitely think about it. Think, I'll give you 2-3 minutes, first figure out what's happening. Then I'll show you, then I'll give you time for the graph. So figuring out what's happening is one part, drawing the graph is another thing. This is an advanced worthy question, this is. Think, take 2 minutes, first try to figure out what the hell is happening. How does this affect the problem and all, and then let's see. Anyone didn't get the diagram of the question, please ask. Hmm. Think, just to give an idea, initially, right, if you put water, the capillary action will dominate, isn't it? So all the water will be pulled in by the capillary only. There'll be no water on the right hand side. So until and unless you reach a certain height, water won't be there on the right side only. The 2 pi s cos theta will keep pulling the water till it reaches the certain height, and then water will accumulate on both the sides. That's how it starts. Think, take a minute more, then I'll show you. Figure out what's happening with the whole thing. The analysis is more important. Let's see what happens. So initially what happens, the moment the liquid falls here, all the liquid will be pulled by this guy only. Getting it? There will be no liquid here. Initially all liquid goes into capillary. Then this will happen till when? This will happen till this meniscus will form here. This will keep on pulling the water. We know that thing, 2 pi rs cos theta. So this will form the height h. We know that result here. H is equal to 2s cos theta by rho gr. Remember the capillary thing? Up to this point, it will go up. Getting it? And remember here, H2 is still 0. H1 is this. So whatever water you're keeping, it will just keep on going till here. Now what happens? Now any liquid that you will keep, now see the capillary will say, boss, I can only lift till 2 pi rs cos theta. Any more liquid that has to be shared between me and the other pipe. So as you're pouring liquid, this is what you'll notice. Let's say if this side the height is increasing. If this is H2, this meniscus will go up. This will be H1. Meaning, see, remember that question we did, the 12th question? If you had taken two different radius on both the sides, what is the difference in height? This, na? And for the big one, this term will be 0, isn't it? Because it is too big, the radius. So what you'll notice, up to this height, whatever is this difference will be 2s cos theta by rho gr. Make sense? So both the sides will start going up at the same rate, but the difference in height will be always 2s cos theta by rho gr. So whatever increases on the left, the same amount will increase on the right. But the left height is already initially more. Is this making sense, everyone? If the right increases by 1 centimeter, left also gets pushed up by 1 centimeter because of fluid mechanics. But the extra height will come due to surface tension. Now you continue to put more and more liquid. Now what will happen? This liquid will reach till the top. And if you continue to put more, now what do you think will happen? Will the water come out like a fountain? Remember that blood drop I just showed you, you get a bulge. So if you keep putting more and more liquid, now this liquid here will form a bulge here. If this pressure is P naught, this pressure will be P naught plus 2S by R. That means to balance this height, the liquid will actually go above the hole. This is like that, boat with a hole question. If this height is some H dash, then the pressure here will be P naught plus 2S by R will be P naught plus rho G H dash. So we get H dash is equal to 2S by rho Gr. Again, a height of a meniscus. Is this making sense? Now, if you exceed this height, now if you continue to put more water, now the bubble will burst. Now the liquid comes out and you're done. Whatever liquid is coming from the left, everything will leak out. H1 and H2 have become constant. But H2 has become greater than H1. H2 has become greater than H1. Is the story making sense, everyone? Is the whole scenario clear what happened? So initially all the liquid will go into the capillary. This will happen till when? Till it reaches the height of the meniscus, the 2s cos by rho gr. Once you reach this height, whatever liquid comes in, that will be shared by the left and the right. So they will rise at the same rate. This will happen till when? Till the left one reaches the top. Once it reaches the top, left side will not take any more liquid. All the liquid will go to the right side only. So that height will keep on increasing till it reaches a height h dash. Now the bubble will form an outward bulge. This kind of becomes like this question, the boat wala question with a hole. So once the height reaches this h dash, it will burst and the water comes out and then you're done. Whatever water is coming from the left will leak from here and you're done. Is this clear area? Now can you draw the graph for this? Try. I'll give you a minute now. Now can you plot H1 and H2 versus time for this? This is what I was saying. Scenario is one, drawing a graph is another story. We know it is increasing, but are they increasing at the same rate? Think. I'll give you a minute or two. Get the graph. Let's see. I'll show you. Let's see. First of all, whatever liquid you're pouring in, this will increase. This is H1, red line. Right? This is 2s cos theta by rho gr. Till this point, this liquid is doing what? This is 0. So till here, all the liquid goes into the capillary. Till then, H2 will be 0. So after this point, what will happen? Both of the liquids will be shared between them. But understand, the right side container is very thick. So do you think the height will still increase at the same rate? Because the right side container is thick, they will not increase at the same rate. They will increase, but at much slower rate. So height increases at a slower rate because the liquid is shared between left and right containers, meaning left and right pipes. Height increases at a slower rate. The slope should change. So liquid is shared between the two sides. So even this guy will start increasing at the same rate. Now see, heights are different, but they're increasing at same rate. This will happen till when? This will happen till it reaches the top. So, and this guy is done actually. और कुछ नहीं कर पाएगा, and then this becomes constant. This is your H1. Clear? What will H2 do now? Now see, once this thing liquid reaches the top, now all the liquid will go only to the right side, isn't it? Previously both were sharing. Now all the liquid will go to the right side, but understand the right is still a big thick container. So it will increase, but at a little faster rate. Giving it rate of increases slightly. Rate of change increases. Slightly, since all the liquid goes to the right side. These are the things you have to be, analyzing and putting there. This will keep increasing. It will exceed this, and then you reach a certain height, and then it becomes constant. So this is the point when the liquid starts leaking. So once the liquid leaks, heights will become constant. This is a graph for H2, everyone. That's how it looks. Check it out. It's all lines, but slopes keep changing. Good, no? I think someone got the graph right then. Any doubts on this? So understanding the whole situation and putting the graph, that's what makes this question really good. Any doubts? Anyone not convinced with the graph or the situation? Anything that you're not clear, please ask. Clear, Parth? Ahana, got this? Ansh? Clear with this? Arya? Arush? You're sleeping क्या? Rehan? Diagram में कैसा दिया? देख. So we are assuming there is nothing here. So first it starts leak from here only. Or
No,
you're saying this height is not sufficient for this to leak.
sir, so it's leaking because of pressure difference or
Eh, because of the pressure difference, that the bubble will burst.
so not necessarily it reaches maximum height of H1.
Then the other side will leak. It doesn't matter. Either way, the thing will stop.
Obviously.
Height has to stop. That's the reason. The approximate graph, we don't have exact details. Clear? But from the given graph, at least this much is clear. H2 is greater. Next one. So till now, what you have taken is all cylindrical pipes. But what if I change the shape? What if instead of a cylindrical shape, if I take two parallel plates? And you place it on a liquid. So if two parallel plates are placed on a liquid surface, surface tension is rho, contact angle theta. So what will happen? The liquid actually goes like this. So instead of forming a spherical shape, it would form something like this. It forms a cylindrical meniscus. This is height, and this is d. Can you visualize the shape how it is? Think of like this. When you're carrying a patient on a stretcher, how does it look like? Getting it? This is how it looks. Now, if you can see my screen, this is how the shape looks, isn't it? It's like a stretcher. No? So this surface is pulling this way, this surface is pulling this way, and the thing surface is like this. Able to see the surface? It's a cylindrical surface. It looks like this. So in a spherical thing, you got a trampoline. Now this thing is like a stretcher. If you have a patient there and if you're pulling it, this is how the surface would look. Kind of like this. I didn't draw it well, but yeah. So this will pull like this, and this surface will pull like this. It's a cylindrical meniscus. Something like this. So the question is find height h. Two parallel plates with a small distance between them. Placed on the surface. Two questions. Find h. Second thing, something happens here. The planes won't be in equilibrium. Plates won't be in equilibrium. So find F external to keep the plates at rest. Find F external on each plate to keep it in equilibrium. Idea is still the same. You draw the FBD of the liquid and then you see the force is equal to mg. The same story there. Length of the plate you won't need, it will cancel out. So instead of a cylindrical thing, now we have a this thing. Parallel plate that will give cylindrical meniscus. Let's see. Yeah. So if you look at the shape here, this is how it would look. So this guy would be S into L. This guy would be S into L. Remember, this is theta and this is theta. This is mg. This was d. Let this length be L and this height be h. Again, we are always taking height till here. We're neglecting that meniscus. This is the FBD of the liquid. So the vertical components to SL cos theta will be mg. To SL cos theta is rho length height dg. It kind of looks like meniscus ka formula. The only difference being instead of radius there is a d plus. Now, if you draw FBD of one plate, and if you look at the forces on this, I will take the right plate. Now look at the forces on this plate. So we have liquid till here. So the liquid is pushing it. This is the force due to the liquid, which is pressure of center of mass into L into height. Now we know at the base level, the pressure is P naught. So here pressure of center of mass will be P naught minus rho G H by 2 into LH. That's the force due to the liquid. From outside, the atmosphere is pushing it, which is P naught into LH. And the surface tension, if you see, it is pulling up with, actually it is pulling down the plate with SL cos theta. And it is pushing inside with SL sine theta, Newton's third law. So in order to stop all this from happening, you need to apply an F external force this way. So therefore, F external will be that P naught LH term will cancel. You end up with SL sine theta plus rho G H square L by 2. That's your answer, everyone. Just try to take one plate. You won't get 2 SL, right? You get only one SL.
Yeah, but won't there be meniscus on the outside of plate?
Here you're saying? सही बोल रहे हो, वो भी होगा एक. So this will climb here also, na? So that guy will pull which way? This way, right? They'll cancel out, na then? So actually our better tha ye. Then the answer will be even more better. Then this will be only rho G H square L by 2. This is the force due to outer meniscus. You're right. You had to include that. Yeah, normally I should take theta 0, so it would have mattered, but okay. SL cos theta, there is no one balancing it. So we are assuming the plate is remaining in vertical equilibrium. We are only interested in horizontal. वो है मतलब vertically there's no one balance. The plate will try to go inside. So someone is holding it vertically. So maybe I should have said F external horizontal. सही बोल रहा हूँ. I have to include that also. SL cos theta in the vertical direction. 2 SL cos theta actually. Clear, everyone? So there's a liquid pushing from outside, atmosphere pushing from inside, and there's a surface tension also. So the thing is, if you don't apply F external force, you know what will happen? Just look at the plates, okay? If you see here, outside pressure is P naught, P naught, P naught, P naught, so on. So here the pressure is P naught, but as you go up, the pressure actually decreases. It's P naught minus rho G H. So the plates, what will happen is if you don't apply that F external force, the plates will become like this. The plates will get closer. They won't remain vertical, they will come towards each other. Is that clear, everyone? Let's see, last one. So instead of keeping the plates parallel, what if I keep the plates at an angle? Like this. Imagine your door, okay? Like opening a door. So the two plates are at an angle alpha. And now if you put it on top of a liquid, you will notice the shape will look something like this. This is how the shape would look. Because if you look at the formula here, this is proportional to 1 by d. D is the distance between the plates. More the distance between the plates, lesser the height. So here, as the distance increases, the height continuously drops. I hope people are listening instead of playing with nails. So please focus. If playing with the nails is the most important thing, then I don't know why you're attending the classes. So And whatever I'm teaching you all is advanced stuff. So you're seriously serious about JEE and advanced stuff, then you need to focus. You can't focus for 2.5 hours class. Then I don't know, like tomorrow you'll go to IIT and exactly what are you planning to do there? And you're planning to compete at a national level. So yeah, but if your plan is just to study in KJ Somaya and all, then it is fine. What you're doing is completely fine. So please play around, don't study much, do time pass. Okay, KJ so maybe you have to pay donation fees. So here S is your surface tension. Theta is the contact angle. So what we want to find, this curve which is there, I want you to find the equation of this curve. That green shaded thing, that thing which is going down, find the equation of that. Find the equation of the liquid surface. Let's get this. How do you find that green ka thing, that curved surface ka equation in 2-dimensional? How do we do this? Consider an FBD like this. At a distance x, take a thin slice dx. Consider this to be origin. Let this be x-axis. So when you take a small slice here, it's like a small cuboid. It's like this piece here. Can you visualize? Now, what are the forces acting on this? This is the surface tension force, S into dx. This is the surface tension force. So if I just draw the piece again, this is how it looks. This is dx. This is x into alpha. This is the y coordinate. That is the height there. And what are the forces? The surface tension force is acting like this. Surface tension force is acting like this. This is S into dx. Remember, this is the contact angle. And your weight mg. End of the story is still the same. So 2 times S dx cos theta is balancing the mg of this small piece. So mg of this small piece is density, and the volume of this is dx, x alpha into y into g. Dx goes off. You end up with 2s cos theta is rho xy alpha g. So we get xy is 2s cos theta by rho alpha g, which is actually constant. S is constant, theta is constant, rho is constant, alpha is constant, g is constant. What is this? An hyperbola. Xy is constant, is PV is equal to constant. It looks like an hyperbola. Won't it be 2x alpha? Why will it be 2x alpha?
So the base of the right angle triangle is x alpha, right?
This is x alpha, na? Huh?
So that's the one triangle, other triangle.
Which triangle are you talking about?
So x is forming a right angle triangle with the bisector of alpha. Like,
Where did you get 2x alpha, right? Actually, this length is x alpha, right? Length, breadth, and width, right? This distance is x, na? You're talking about this length, isn't it? And
okay,
this
so
angle is alpha. Hmm. Sure, na? Yeah. There, that is about it. So that's about surface tension. With that, we're done with the chapter also. So next class, when we catch up, we'll be starting off with elasticity. That's also a small chapter. Mostly should wrap up in 2 classes. But it will have a lot of things with thermal expansion also in relation, few questions from there. So we are done with fluid, viscosity, surface tension. This entire thing is one chunk. So you can start solving. If you have not started, do start solving. Don't take too much time. We will wrap up this thing in another 2 classes next one. So we'll catch up on Thursday again, as usual at 5:30. So any doubts, anything, you can stay back and ask. Also, free to leave. So take care, stay safe. See you on Thursday at 5:30.